Swayam Prabha. Digital India. Educated India.
Yesterday we talked about what is the velocity at which a particle is settling, and I wrote this equation. Okay, let me. So you can see that it's proportional to diameter square, and rho is the density ratio. Rho is the ratio of particle density to fluid density. Now you can see that this sort of settling velocity, when a particle is shedding vortices, is going to be complicated, because it may not even come down straight, it just goes. Now if a particle is sort of dancing around, even defining what is the settling velocity becomes a complicated thing. So I want you to think about it. You could do in several ways. You could say, well, settling, its velocity keeps changing, it goes to the side, etc. So one way is to say, okay, I track the particle from here to here, how long it takes to come, distance divided by time is the velocity. Okay, so that's one way. Or if you have particle tracking technique, you can calculate, okay, how much it moved in 1 second, a very short time. You can calculate velocity of one particle as a function of time, and you can average it over time. Or you can find the settling velocity of many particles and you can average. So in other words, when particles are tiny, when their Reynolds number is small, things are easier. When particles get bigger, like in fluidized bed kind of applications, a lot of things that we take for granted becomes very complicated. Okay, so that may be what I should say. So in this case, you should think of, okay, you take the particle velocity, you measure the velocity, and you calculate what's the vertical component. Okay, Eg is nothing but unit vector in the gravity direction. Okay, and then you average. Okay, you average over many particles, or you average over time for a single particle, or you average over time and average over 10 or 20 or dozen particles. That's how people calculate the settling velocity. Now settling velocity is, I don't know, none of you mentioned this, but if you are working on environmental kind of things, sedimenting particles, etc., it becomes an important quantity. Okay.
Yeah. So this will depend on the initial condition also, because yesterday in the online lecture there were ellipsoidal particles that were falling down, and depending on the initial shape, whether they are horizontal or they are sort of vertical, then this terminal settling velocity will be.
Absolutely. This everything is for a sphere. So for a non-sphere, it becomes even more complicated. Yeah, yeah. Orientation, etc., will play a role. Yeah.
What the 5 RES?
What is that?
5 RES.
Oh, fear. That's the Reynolds number, finite Reynolds number correction. So you remember, this is one correlation, because most of what we are talking about is what happens when particle Reynolds number increases. So this portion is only coming from a Stokes.
Terminal settling velocity.
This is the Stokes settling velocity, but it's not will be accurate if your particle is settling at a finite. And this, if you put in, you will get a better estimate of the settling velocity. So Stokes settling velocity is only good for very small particles. So as you can see, when Reynolds number is very small, big phi becomes 1. Okay, when Reynolds number is very small. So only this correction you need to do. you need to do only for finite Reynolds number. So, what I want to say is a few points I want to make. Okay. Now, this portion has to do not with particle creating turbulence, but I want now to switch gear and think about particles settling in turbulence. And this could be small particles, sub-Kolmogorov particles, could be. Okay. Now, the question is, you have a bucket and you have turbulent flow, and you have particles in there. They are far apart. They are not interfering with each other because we are now still thinking in terms of one particle. Okay? In other words, particle-particle interaction is not. So, the question is, they are falling down. And you use any of the method that I talked about in the previous slide. You find how long does it take for the particle to go through some depth, or you measure the velocity, settling velocity of every particle, and you average over the particle or track particles and find, it does not matter. So, you are finding some average settling velocity. You want average because you are in a turbulent flow. Okay. So, things are changing. Easy thing is that particle in a still fluid is falling down. Let us say it falls down with 1 centimeter per second, but you put it in a turbulence and he is in a 2 meter per second upwelling. He is going up. He is not, because he wants to go down 1 meter per second, but the fluid is going 2 meters per second. So, he is going now up 1 meter per second, because he is falling down through a up moving fluid. On the other hand, he is caught in a downwelling flow of 2 meters per second. He is just zipping down. Okay. So, now every particle is falling down at any instant in a different velocity. Okay. They are not lockstep. Okay. So, the question is, in such situation, settling velocity is a random number. Okay. It's varying. So, you can only talk in terms of average. Average over time, average over many different particles, you can do many things. So, we can define an average. That's what I was writing here. So, the question is, if you do an average, will it be equal to, this is called still fluid settling velocity. In other words, quiescent fluid, particle settling down, and that is this formula. We have a formula. It is good for quiescent fluid. Question is it still correct for a particle in turbulence? Okay, that's the question we are asking. The answer is no, there is difference. So, people have measured that settling velocity sometimes is larger. Again, this is not fully settled problem. I mean, there is no one answer will tell, okay, this is what is going to happen. So, it is still a lot of research going on. The reason is there are many competing mechanisms. Some try to increase the settling velocity, some decrease the settling velocity, and who wins is the question. So, sometimes the settling velocity increases 10 times. Okay. I do not know if you remember, I talked about what is called hypopycnal flow, where sediment comes from the river and goes on top. That sedimenting velocity is 100 times larger than what this would predict. Okay. So, this is very important, because if you have a muddy river goes into the ocean, how far that mud will settle is an important question. If it settles 100 times faster, then that muddy river, all the mud has fallen down very close to the river mouth. Otherwise, it could go hundreds of kilometers into the ocean. So, it is important to some people. So, sometimes it increases, and sometimes the settling velocity is very, very small, and this is a big problem. For example, in mining industry, there are laws like you have dredging, so dirty water is there. you got to let those dirt settle down before you dump the water. Okay, phosphate mining, many different mining industry. So settling is a very important business. There, what happens if your settling velocity is five times lower? That you have to find ways to increase the settling velocity. So it's an important thing. So the fact that things don't settle at this settling velocity is a big difficulty in prediction, in control, and so on and so forth. Okay. So let's go and talk about why these three mechanisms will decrease settling velocity. Well, nonlinear drag. Nonlinear drag, I don't know how many of you have encountered this in your work. If you have a nonlinear, say in this case drag, if you take nonlinear drag calculation, calculate drag at every instant and then average. So in other words, you calculate drag and then average, versus you average the relative velocity and then calculate the drag on it. They are not the same. So in other words, nonlinear operations and averaging don't commute, so you can't swap. Okay. So as a result, what happens is that nonlinear drag, high drag matters more than. So in other words, what we are talking about, say there is an average. So when I talked about upwelling flow, downwelling flow, etc., think of a particle whose average Reynolds number is 1. But sometimes it's going to be half, sometimes it's going to be 2. The drag when it is falling down fast at 2 is much more heavily weighted than the reduction that you see when Reynolds number is half. So in other words, they don't perfectly balance each other. So higher Reynolds number matters more, therefore you end up getting more drag, therefore it decreases settling velocity, and this is the nonlinear effect. In other words, if instead of falling down at the same velocity, if it keeps changing its velocity, high velocities will create more drag, and therefore it will eventually slow down the particle. So this is called the nonlinear effect. Okay. The loitering effect and particle trapping are very similar. What happens if you have a upwelling flow? It is exactly at 1 centimeter per second, and the particle settling down at 1 centimeter per second. It's not going to move anywhere. It's going to stay there for a long time. So particle could be trapped. In other words, settling velocity could go to 0 if they are locked up in eddies. Okay, dead zones. Okay, well, relative dead zones. So in other words, particle has no effective velocity because it's seeing an updraft, and that's why, you know, in atmosphere, when you ask there is so much pollution there, why is it there? It never settles because atmospheric turbulence keeps it stirred up. Okay. The other thing, we did some interesting research on coughing and sneezing, talking, etc. Puts out lots of, this is especially during COVID period, why airborne diseases spread. Okay. These airborne things, they quickly evaporate. They become 10 micron and 50 maybe micron size particles containing these viral things, and in a room like this, it just stays there for an hour. If you use the settling velocity, you may say, oh, all of them should have fallen down in a couple of minutes, but no, it doesn't. The air turbulence is good enough to keep them well stirred. So you can again think of that settling velocity being much lower because it doesn't settle. Okay, so those are the effects why average settling velocity can be lower. Now it can be higher, and I said that it can be substantially higher due to many different effects. One of them is trajectory bias. Okay, this is a very interesting thing. So imagine that you have flow eddies like this. I mean, this is not how turbulence looks like, but let's just imagine that I'm sorry. Okay, so let's say you have a eddy pattern like this. I've mucked it up. Okay. Okay. So this eddy is going this way. 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 I'll try again. Okay. Okay, so just a simple eddy pattern, and now let's think of a tiny particle. He goes down this way, but here the fluid is going up, right? He becomes unstable and he sort of goes this way. Then he comes back this way. So this is called fast tracking. So I said that if the particle is in an updraft, he can be carried by the updraft. But what happens is that, imagine like you have a ping pong ball and you are putting updraft, it's not going to stay there, it wants to go to the side. And that's exactly what happens here. The fluid is saying go up, and the particle escaping that and then bypasses and then wants to go down. So this is called fast tracking or trajectory bias, and that happens. So when you have turbulent eddies going on, theoretically I was saying, oh, updraft will keep the particles up and downdraft will keep the particles down. That's in some sense true, but sometimes depending on the Stokes number, particles can always keep trying to catch the downdraft flow, and he keeps settling faster and faster. So sometimes it happens, okay, and therefore trajectory bias can increase settling velocity. The other thing is one of the most important thing that I was talking about earlier is that, so imagine that you have a sediment laden fluid. So these are particles in there, and this is clear fluid. This fluid here, since there are particles, heavier, and this fluid outside is lighter. Therefore, this once a little blob or fluid protrudes, this is the two-way coupling. This guy is slightly heavier, these blobs are a little heavier, so it's light fluid here, light fluid here, light fluid here, in between your heavy fluid. So he wants to go down faster. Is the two-way coupling effect is that the gravity will pull it down, and this blob may go down at 100 times the velocity of this guy. Okay. So in other words, there is really very complicated, and this you may call instability or onset of turbulence or whatever you want to call it. Okay. So in other words, there may be many mechanisms. Even simple things such as settling velocity doesn't follow some analytical expectations. So turbulence is created, existing turbulence can completely modify settling velocity. Okay. So I just have a little bit more details on some of the stuff that I talked about.
Sir, just one question. Yeah. So average settling velocity decreases. That you have explained this non-linear drag.
Yeah, yeah. So to analyze this nonlinear drag effect, you have to look at the equation of motion that we have studied. So this is nothing but Newton's law. So mass times acceleration of the particle equal to the forces that we talked about. Of course, I have ignored Bassett history force, etc. So what we have here is quasi steady force and just gravity force. So I have ignored all the added mass, all those things, because I wanted to make simplification, and what we have is here the simplest thing, even though it's an unsteady problem, let us say it is dominated by quasi steady drag, and then this is the body force and the buoyancy force, etc. So, these are non-dimensionalized, and then what you have is that Vs is nothing but the non-dimensional settling velocity, and tau p is the particle time scale that is given here, and then phi Re is nothing but the formula that I gave for nonlinear drag. So, this is a very simple equation that tells how a particle will settle. Tau p, let us say, is a constant roughly, and settling velocity is a constant. Now, what really changes is this guy, the fluid velocity at the particle. So, in other words, in a turbulent flow, the particle will see different fluid velocities at different times, and if I sort of massage this equation, so this equation is the same as this, so you get this kind of a form. Okay. The question is that then you can take this and you can study what happens in the limit of large Stokes number, tau p gets very large, and so on and so forth. So, what happens is that,
like change in velocity takes place because of the change in velocity of the fluid.
exactly. So, this changing velocity in this case, this u c is nothing but fluid velocity at the particle location. So, particle is going to different parts of turbulence. Sometimes it is going up moving velocity. Now, this is the particle velocity itself, that is also changing, okay, depending upon whether it is responding to the turbulence. Okay. And this part is a constant because this is the settling velocity, etc. So, in other words, this simple equation is telling us the fluid is changing, okay, as the particle goes to different parts of turbulence, it is experiencing its motion is changing because the fluid it sees is changing. Okay.
So, trajectory bias and nonlinear bias like are the opposite things. If the fluid is opposing the particle velocity, and the settling velocity decreases, and vice versa.
Not quite. Say for example, what I wanted to point out was, if you have a particle and let us say it is in a one dimensional flow. Okay. Okay. So, it just sometimes the fluid is going up slowly, sometimes fast, sometimes down, sometimes down. Here the settling velocity will decrease, here will decrease a lot, here it will increase, here it will increase a lot, because this particle as it falling down, it is going through different turbulence. Sometimes it is going through upwelling flow, sometimes downwelling flow. So, it is visiting a lot of different regions. Okay. Therefore, what you will find is that here Reynolds number, here, the Reynolds number is not the same. Okay. It is a function of time. In a still fluid, let us say you have a Reynolds number. So, that depends on the settling velocity. Okay. Now, if it is in an updraft, your Reynolds number will increase because particle wants to go down, your relative velocity is opposing. Okay. So, the Reynolds number will be large, here will be larger, here will small, and this will be smaller. Now, the way to think of this is, if the particle in a calm fluid, if it is coming down at Reynolds number say 10, sometimes it will increase to, in a turbulent flow, it could become 9 or 8, 11 or 12, it's just constantly fluctuating. Okay. Now, in a nonlinear drag, the drag at Reynolds number 10 or 9 or 8 or 11 or 12, they are not the same. The drag coefficient keeps changing. Higher the Reynolds number, larger the drag. The drag coefficient may be small, but the drag itself will be larger. So, now you are averaging, when I talk about average settling velocity, in a way I am averaging the drag. What's the average drag? So sometimes I am averaging over increased drag, highly increased drag, decreased drag, significantly decreased drag. So in other words, I am averaging. Okay. When you average, is it that average, will it be the same as that of a particle falling down in a quiescent fluid? The answer is no, because the nonlinear effect, higher the drag weighs more important than the lower drag portion. Okay. So one easy way is that, let's say if you have a number 1 and you sometimes have half and sometimes have 2, and then 2 square and 1 square, when you add, they may not be equal to 1 square. So in other words, nonlinear property when you add doesn't add up easily. Okay. And in this case, what happens is that the higher drag weighs more, and therefore you have overall reduction in the settling velocity.